Hi, folks. Welcome back to Physics with Captain Rod. I'm making this video here to be kind of an introductory video about a topic called power, which I'm going to write right here. And I got a couple cases here we're going to discuss. Okay, case one is this child uh, biking up this hill at a speed that we're going to assume to be constant for this discussion here. And I tried to show that with my motion diagram here, little snapshots of time. Click, 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 click. Imagine this child starts here at what I'm calling position one and ends up here at position two over a time frame of 4 seconds. And I threw out a mass here, and this is intended to be a mass of the child bike combination, and I just threw a number at it for the sake of discussion here. Now, if we think about this in terms of energy, if we put a datum here, then our PE1 term would be 0 for that child. And if we look at position 2 and we calculated a potential energy, assuming the child ended up a height of 10 meters higher, and I just picked values here up above the datum. I guess I have that a little long, but if we calculate a PE2, I get 9,800 joules coming from mGh. So this ROC, this stands for a rate of change. So anytime a quantity is changing, you can calculate, or I should say a natural question to ask is, well, how fast is it changing? In this case, the potential energy of the child went from 0 joules to 9,800 joules, and it did so in 4 seconds. So if we calculate the change in energy, and divide by the change in time, that would be 9,800 joules over 4 seconds, and we get a number. And that number is about 2,450 joules per second. And that number is describing how fast the potential energy of that child is changing. Each second that goes by, the child's potential energy, or I should say the potential energy of the child Earth system, is increasing by 2,450 joules. Now, I would also point out that because in this case that was a constant speed problem, this change in energy actually represents the total change in energy of the system. Keep that in mind here as we talk about case two. So case two, we're going to chat about this car, which we're going to assume starts from rest in this example, and then the driver hits at gas. I guess it's Christine or something because there's no driver there, but that's okay. So the driver gets at gas, and we're going to imagine that 4 seconds later, the car is moving at 5 meters per second. And I just picked times here in numbers to kind of illustrate as an example here. We're going to imagine that the system here is 1,000 kilograms. And now what we're going to do is focus on the kinetic energies here. If we just put a datum right through here, all potential energies are 0, and kinetics are the only thing to talk about. And if it starts from rest, the KE1 would be 0. The KE2 I've already calculated, 1 half mv squared, and I got 1,250 joules out of that. Oops, I'm going to double check that here, make sure I didn't miss a 0 there. Oops. Yeah, I think I missed a couple. Yeah, I did miss a 0 on there. Oops, I'm going to have to go ahead and add a 0. My apologies for that, but that's okay. 12,500 joules. So the car started with a kinetic energy of 0, ended up with a kinetic energy of 12,500 joules in a time frame of 4 seconds. So a natural thing to ask is, well, how fast did the car's energy change, right? That's a rate of change. I guess I got to add a 0 to this. So the change in energy, in this case the kinetic, would be 12,500 joules in 4 seconds. Add a 0 to this, I'm sure. And a 0 here, and that's perfectly fine. Actual numerical value is not super important for the discussion, but anyway, if you do the division, you get 3,000 or 3,130 joules per second. So that's the average rate at which the car's kinetic energy is changing over time. Now, a joule per second has its own little pet name. It's called a watt. So going back to these two things we calculated, this 2450 can be expressed as 2450 watts. And same thing here, this 3,130 joules per second can be expressed as 3,130 watts. And that's an example of what's called power. Power, I like to define it like this. Defined as rate of change in energy of a system. We'll just say rate of change of energy. When you calculate it, you can do so by taking a change in energy over a change in time, or you can calculate it by work over time, at least for a basic problem in mechanics. Because in both cases that we just looked at, there is some sort of external force doing work. Work is what changes your mechanical energy. So either one of these is acceptable. You can also, by the way, define power as the rate at which work is done. I like to define it like this because this takes into account later on when we talk about heat transfers and other types of energy transfers. This is a more, I think, generic way to think of power. So, just meant to be an introductory video, conceptual video about power. One thing I'd also point out, the two examples I talked about, I kept these kind of separate. In case one, only the potential energy is changing. In case two, only the kinetic energy is changing. But that doesn't, need to be the case. You can change both at the same time. Imagine our car on this fella's hill, and the driver hits the gas in such a way that the car is accelerating up the hill. In that case, you would have changes in kinetic and changes in potential at the same time. So anyway, it's not just a potential or kinetic thing. This delta E here is the total change in energy of the system. So that's what power is. It's the rate at which energy is transferred. It's another average rate of change. I hope that was okay for at least an introductory video.